So let's talk about how we could do definite integrals using numerical methods, okay? We'll discuss 3 different numerical methods here. And so this topic in general is called numerical integration, okay? You're computing the area not using symbolic methods where you take the antiderivative and get an exact form, but you approximate it by various methods. So take a look at one method called the midpoint rule. And here, I mean, you ran into this when looking at the Riemann sum. What you basically do with the midpoint rule is you break up your interval of integration into subintervals. And then for each subinterval, you'll take the midpoint of that subinterval and evaluate the function there. Okay? That will give you the height of a rectangle. And the width of the rectangle will be the length of the subinterval. Okay, that'll give you an area for the rectangle, and you could approximate the definite integral, which is the area under the curve, using a number of rectangles. And of course, the more rectangles that you get, that you'll use, the better your approximation will be. And so here's the general formula for the midpoint rule. We break up our subinterval into n. We break up our interval into n different subintervals, and we evaluate the function at the midpoint of each subinterval. So it looks like that. You'll take the midpoint of each subinterval, multiply it by the width of the subinterval, and add all of these areas together. Okay, here's the general formula right there, where delta x is the length of the subinterval, which you get by taking the final point minus the initial point divided by n. Okay, so you'll take b minus a, which is the length of the whole interval, divided by n, because that's the number of subintervals. You have your x naught is a, and so xk, basically the x associated with the end of the first subinterval. So x sub 1 would be the end of the first subinterval. X sub k would be the end of the kth subinterval. There goes your formula for that. And you have mk, which is the midpoint of the kth subinterval. Okay? And so that's how you'll approximate this. Let's take a look at a concrete example here. So we want to approximate the integral of x squared from 2 to 4. And we're going to use the midpoint rule with 4 subintervals. Here are a is 2, b is 4, and n is 4 as well. Delta x, the width of the subinterval, is going to be 4 minus 2 divided by 4. So the length of the subintervals is half. And x naught, where we start, is 2. x1 is going to be 2 plus k equals 1 here, times 1 half, so 2.5. x2 is going to be 2 plus 2 times 1 half, and so we get 3. And then 3.5 and 4 using, that similar formula, or we could have just guessed it since we're just adding a half each time, right? For the midpoints, we could use that formula, so x naught plus x1 divided by 2, and that'll give you 2.25. You do the same thing for the second subinterval, the third subinterval, and the fourth subinterval. And M4, the approximation of our integral, our definite integral above, using 4 subintervals, we will have these terms to sum, the areas of each of the rectangles. Fm3, for example, is m3 squared because f is equal to x squared. And then we just input all of the results that we have above, and we get that the approximate value of the definite integral using the midpoint rule is 18.625. So let's talk about another way to do to use numerical methods to find the definite integral. The other one is the trapezoid rule. Okay, and what you're doing differently with the trapezoid rule is instead of having just a flat top for your rectangle, you're going to have a tilted trapezoid, okay? And what you're going to do to get that trapezoid is for each subinterval, you'll evaluate the function at one end and then evaluate it at the other end of the subinterval and draw a line between those two. Okay, you could see that the function in purple there isn't exactly that line, but it's a way to approximate. Okay, and you'll get the area. So for example, for this trapezoid here, the area is here. Okay, for that one you'll have fx naught here, which is the length of one side of the trapezoid, and fx1 for the other end, okay, the other side of the trapezoid, and the width of this trapezoid is delta x, and so the formula for the area of the trapezoid is above there. And you'll add these together, okay, you'll add all of the areas of the trapezoids together in order to approximate the area under that curve, and you end up with this formula here. And I want you to pay attention that you get a 1/2 for the first point you evaluate the function at, and a 1/2 times the height of the last point you'll evaluate the function at, times delta x, the width of the subinterval. Okay, but in the middle you don't have a half there. And what's going on there is, you could sort of see that if you have a 1/2 fx naught plus fx1, okay, for the first trapezoid, okay, and you'll get for the second trapezoid 1/2 fx1, okay, plus fx2. And you could see that when you add this 1/2 fx1 with, this 1/2, once you distribute that half fx1, you'll get just fx1. And so that's what's going on. Whereas there's nothing to compensate for the first 1/2 of fx0, and nothing would compensate for the last one, trapezoid. Okay, and so that's what's going on. In the middle, you're adding the halves together, and so you get a full fxk. And at the ends, you have that half. Okay, so that's the formula. And we could take a look at integrating the function that we had above there. So instead of fx, it should be x squared there. Okay, and if we use this same formula that we see right here for the trapezoid rule, we'll get these terms. We're using 4 different subintervals, and so you'll have, once you plug in x0 into the function, which is x squared, you'll get 1/2 x0 squared there for the first term, x1 squared, x2 squared, x3 for the middle terms, and the last one another 1/2. Okay, so that one, it's not clear, but that's a 1/2 there. And you plug in your values for the different x's, and these are found in exactly the same way that we did above. Okay, same formula there, and you get 18.75 as opposed to the 18.625 that we got for the midpoint rule. And so this is how you use the trapezoid rule to numerically integrate a definite integral. So a final method that we'll consider for numerical integration to approximate the values of definite integrals is Simpson's rule. Okay, and now before we looked at the midpoint rule, we'll basically take a subinterval, find the midpoint of that subinterval, and then we'll have a flat top and compute the area of a rectangle and add the area of those rectangles. Then we looked at the trapezoid rule, where you're basically drawing a straight line between the 2 points at the end of the subintervals, okay, where the function is evaluated at end of the subintervals. Well, now we're doing something a little interesting. We're approximating the function by a quadratic at the top. Okay, so here are heights. Rather than being just a straight line that's tilted, such as in the trapezoid rule, or a flat line, such as in the midpoint rule, we're going to have a top that's parabolic. Okay, we're going to have a quadratic function approximating the function over a given subinterval. Okay, and how you do that? So if you take a look at these two, if you take a look at these two subintervals, okay, we're going to use a quadratic to approximate that function over two subintervals. All right. Well, if the function has a value of y0 at minus h, and y2 at h, and y1 at 0, and here we're just centering at 0 to make the math a little easier. We're going to get a formula for the area, just like we had a formula for the rectangle and a formula for the trapezoid. We're looking for a formula now if we approximate using a quadratic. So here's the general form of our quadratic. Okay, a, b, and c are constants, and we want to fix that. So what do? We impose constraints. We say that the quadratic must be equal to the function at y0, the left part of these subintervals, and the quadratic must be equal to the function at the right point. So you could see the quadratic at the top there intersects the function. And at the midpoint, it also must be equal. So we impose those three constraints. Okay, we want a quadratic that will satisfy those three. Okay, that's actually equal to the function at those 3 points. If we do that, okay, and solve this system of equations that you see there, we'll get the values of a, b, and c in terms of y0, y1, y2. And of course, you know, y0, y1, y2 are the actual values of the function at those three different points. Okay, we integrate that, and we now have a formula for the value under the parabola given these values for the function there. Okay, and we'll now have this rule, this formula for Simpson rule using n subintervals. Okay, and now what's going on? You have to pay attention here that n must be an even integer for this formula to work. Okay, so you always break up your interval into an even number of subintervals. Okay, just to make this alternation work. And so you'll have fx naught and no coefficient, then you'll have 4, then you'll have 2, then you'll have 4, and then you'll have 2, and then 4, and then 2, and then 4, and then, you know, as many terms as you have, and then 2, 4, and then 1 at the end. Okay, and that's sort of why we're choosing an even number, just so we could write that alternating form there. And it's pretty clear where that 4 is coming from. It's the same form 4 there. But where's that 2 coming from? Well, it's coming from the next term. Okay, if you'll have the next term, you're going to get, it's going to start with a y2. And so you'll add this y2 to the other y2, and you'll get 2 there. Okay, and then this 4 is coming from that. Okay, the midpoint of the interval where we fit the parabola. Okay, and this delta x over 3, where delta x is that value there. Okay, and x sub k is as we're used to. So let's look at a concrete example of integrating using Simpson's rule. We want to integrate that value right there using Simpson's rule. So to do that, we'll break up our interval of pi over 2 to 5 pi over 2 into 4 subintervals. That gives us a delta x, the width of a subinterval of pi over 2. So let's start at pi over 2. X naught is pi over 2. And we keep adding pi over 2 to get the endpoint of the different subintervals. So the endpoint of the first subinterval is pi. The endpoint of the second subinterval is 3 pi over 2. And then, you know, the fourth one is 5 pi over 2, which is where we're ending. Okay? Now we use the formula that we have above there. We'll start with coefficient 1. Then it becomes 4, 2, 4, and then 1. And you'll always have an ending of 4 and then 1 there if you chose an even integer. Okay? You just keep alternating 4, 2, and then you should end with a 4, 1, okay? And we evaluate the function, so we'll have, you know, sine x naught over x naught there, because that's the integrand. And we plug in the values that we computed for the different x's, and we end up with this value here. So that integral is approximately equal to 0.178. So, okay, I mean, numerical integration is all about approximating integrals. And so we want a way to talk about the errors, okay? And what's very important here is that you have a bound on the errors, okay? If you're actually writing a program that will compute the value of a definite integral, you want a way of basically saying, look, I could give you an answer up to the third decimal point that's correct. I can guarantee you that the third decimal place is correct. You need that. You need to have a way of quantifying your errors. Okay, and so let's take a look at how we could do that with these methods. So first, some definitions. Absolute error. So if the c is the approximate value computed numerically and x is the exact value of a definite integral, okay, then the absolute error is this, the absolute value of c minus x. So basically just the difference of them. The relative error is c minus x divided by the correct value, okay? Of course, x cannot be 0. You can't divide by 0. Okay, and so that's just definitions there. And here we have a very important theorem. Okay, for midpoint and trapezoid rules, if we assume that f, the second derivative of f, is continuous on the interval that we're integrating, and that k is a real number such that the second derivative of the function is bounded by that real number. And here's where all the sort of magic and tricks go, okay? You always want a bound. And so we could bound the second derivative, the absolute value of the second derivative, by this real number k on the interval a, b, okay? Now, if we have that, and we're using n subintervals, then we get a bound on the error. So this e is the error for the midpoint rule of this. And that's basically telling you that someone could guarantee you that the error that you'll have, the absolute error, okay, that you'll have using the midpoint rule is this. Okay? Now you can see it's very crucial to get a bound on the second derivative. But what about the trapezoid rule? We can guarantee that the error, the absolute error, is less than or equal to this value if we could get the second derivative bounded by this k. Okay? And so these are our bounds for our error. You could see as delta x goes to 0 or n goes to infinity, right? The error using these methods goes to 0. Okay? And so we have a way of bounding now our results, which gives us a lot of confidence, right? We did make an assumption that the second derivative is continuous and that the function, the second derivative is also bounded. But the nice thing is we now have a way to bound our errors, and we know that if we keep using more and more subintervals, then our errors should get smaller and smaller. And that's really important to say, okay? For Simpson's rule, it's a little more complicated. Here we take the fourth derivative, okay? And the fourth derivative needs to be continuous. And we bound the fourth derivative by this capital K, okay, some real number. And so the absolute error using Simpson's method is bounded by this value. Okay, bounded means it's not equal to that. Okay, you can't say that the absolute error will be equal to this, but you at least have an upper bound of what the maximum that your error can be, and that's good enough, right? The maximum, and thankfully it could be a lot less, but at least you know the maximum. So you could say, this is correct up to this decimal place, all right? And so if we were to compute the relative and absolute errors using the trapezoid and midpoint rule for x squared, well, the exact value is 56 over 3. That's just by taking the indefinite integral and evaluating it from 2 to 4 using the fundamental theorem of calculus. Okay, you get 56 over 3. And we found that the midpoint rule gave 18.625. And so this gave us an absolute error of 0.0417. Okay, that's the absolute error. And the relative error was 0.00223. For the trapezoid rule, we got an absolute error of 0.0833 and a relative error of 0.00446. It was not necessary that the midpoint rule gave us better results than the trapezoid rule. You can't say in general that this method will give better results than another. You do have these bounds, but in general, you really can't say that one will give better results than the other, okay? It just depends on the function there. But at least we have the bounds, and here it turned out for our case, the midpoint rule gave better results than the trapezoid rule. Suppose for Simpson's rule, so here we didn't use the bounds. We just computed straightforward absolute error and relative error for those two methods. But what about using the bounds? Like suppose, you can prove, or someone will tell you that the fourth derivative of sine x over x is bound by 0.2 over the interval of pi over 2 to 5 pi over 2. Well, then you could say that your error, okay, will be less than or equal to this. Doesn't mean that it's equal to, but your error using Simpson's rule will definitely be less than or equal to 0.0425. Okay, so your final result, you could write, I found this much. So when we did this, we found 0.178 for that. So we could say that the answer is 0.178 plus or minus 0.0425. Okay. So, approximately 25, because you could have other values there for when you evaluate this. But we at least have a bound now, and we know how confident we could be about our approximation.